Hi, I'm Sheridan. I'm the circuitry artist, and this is part 3 of my introduction to electronics. Today I'm going to be going over some of the basic math and some examples, a few symbols, and a few explanations of how the mechanics and the factors all work together. So I'm going to start with our two formulas. Actually, keep you from getting distracted. I'm going to start with our two formulas over here. We have Vir and Piv. V equals IR, P equals IV, or voltage equals current times resistance, and power equals current times voltage. Now, if you're a complete beginner, that probably doesn't mean much to you now. Don't worry about that. I'm about to explain it now. So, voltage is probably the component that we're the most familiar with. If we look at the side of a battery, we see it has 1.5 volts on the side of it. We have 3.7 volt batteries inside of our cell phones, 120 volts AC comes out of the wall, and we have 18 volt drill batteries. So what does that actually mean? What does it mean to have voltage? What does it mean when a battery says 1.5 volts on the side of it? Well, the answer to that question is actually pretty technical and pretty complicated, and it's actually has more to do with chemistry than electronics. But I think for the sake of simplicity, I can explain it in a sort of analogy. So, imagine that you've got a flooded basement, and you have a pump that's pumping water out of the basement through a hose to a storage tank. So, voltage can be thought of as the pressure that the pump generates, and it puts on the water in the tube to flow up the tube and out of the basement. And current can be thought of as the amount of water and how fast it's flowing through that tube. This is kind of a point where beginners get hung up and where experienced technicians actually use the terminology incorrectly because they say that voltage is flowing through a wire. I mean, which, you know, it's sort of one of those verbal shorthands that people do. But in reality, voltage doesn't actually flow through a wire. Voltage is simply the pressure that's put on electrons to flow through a wire, and the current is the actual electrons flowing through the wire. Now, resistance can be thought of as, going back to our pump and hose example, as a kink in the hose that makes it more difficult for water to go through that point very quickly. Resistance can also be sort of thought of as friction in a circuit. Or, I should say, mechanical... No, that's not right either. It's just sort of like friction in a circuit. So say, for instance, that I'm making a circuit here, and I make my complete path. This is actually a symbol for a battery, by the way. I don't know if you knew that before. So, what's going on in this circuit is that we've got 5 volts, and it's being pushed through... It's pushing current through a 400 ohm resistor. So, based on this formula, what we do know is that 400 ohms times 13 milliamps is 5 volts. So, what happens if we have more resistance in it? Well, let's flip this switch. So what just happened there? Why don't we have current flowing through this resistor as well? Well, because we have something in electronics called a short circuit. And a short circuit is when you have... It's when you have a path from one end of a component to another end of a component with no resistance. This is why birds can sit on telephone pole wires or power line wires and not get shocked, because even though their feet are grasping the wire, there is a short circuit between their feet that keeps... So if you imagine this is the bird and this is that power line, you can see that no current is being pushed through that resistance because we have a complete path around it. Now if we open up the switch, now we have current through it. And now what we've created is a series circuit. A series circuit is also known as a voltage divider because if we measure here between the resistors, we have 1.66 volts, which is not the same as our 5 volts up here. So this is how voltage gets divided. So if we want to turn one voltage into another voltage, we use two components in series, and it produces a different voltage in between them. Now, to calculate our total resistance, to calculate our total resistance, since we have two resistors, we simply add them together, one plus the other. And if we have 3, we just add 3 until we get our total resistance. Now sometimes, not all our circuits are series. Sometimes what we have is multiple paths which current can flow through. This is called a parallel circuit, because each path is parallel. Now to calculate our equivalent parallel resistance, we use this formula here. So we have inverted R1 plus inverted R2, invert our sum, and we have our total resistance. If we have 3 resistors, we simply put another R3 to the -1 inside these parentheses, and we do that for each additional resistor that we have in parallel. Now sometimes we have combination circuits as well. So this is a combination circuit. We have 2 resistors in parallel, and we have another resistor in series with the parallel network. And for this instance, we actually have to use both formulas. And first, we always first do your parallel resistances first. Do that first. Now, a handy little shortcut: when you have 2 of the same resistors in parallel, the equivalent resistance is 1/2 of one resistor. If you have 3 of them in parallel, then it's 1/3. You get the pattern. So we have 200 ohms here, equivalent between these two, and 600 ohms here. And we have our voltage divided by into 1 part of 3.75. To illustrate the voltage divider concept a little bit more clearly, I'm going to show you, maybe I can do it this way, yeah. So we have 400 and 200. If I mouse over this resistor, you can see down at the bottom in the little tiny white text, there's a VD. That means voltage drop. That is the voltage between the 2 terminals of the resistor. And as you can see, it's 3.33 volts. And this resistor has a voltage of 1.667. So in a series circuit, all the voltage across all the components, the sum of the voltage across all the components is equivalent to our total input voltage. Whereas our parallel circuit, the sum of each current that goes, the sum of the currents that go through each leg is equal to our total input current. Therefore, it's a current divider. Another handy little thing to notice, little math trick to know about current dividers and forks in wiring, is that when you have current going into a point, the same amount of current has to flow out of a point. And that's true for any component. When you have current going into a component, the same amount of current has to come out of a component. I actually once had an electronics instructor tell me that there was a guy who got shocked by touching one end of a 12-volt battery and nothing was connected to the other end. Which is to say that current flowed out of the battery without current flowing back into a battery. And as you can see, if I disconnect this battery on that end, nothing works. That's because current has to flow back into the battery. But, I don't know. He thought he was right. I thought I was right. He called me Sheldon for that semester, but anyways. So where was I? I covered the math and I covered the formulas. So voltage, one thing to know about voltage is that voltage it lives on a number line. And so this little symbol right here, 3 lines in a triangle shape, that means 0 volts. And so anytime you have any components and any power sources, this means 0 volts. Now sometimes what can happen is you get a circuit with these little 5-volt inputs and these ground symbols in it. Now all that means is that in order to power the circuit, you have to have a power supply that can supply 5 volts and a ground. That's all. It doesn't mean that there's this magical 5-volt node floating in space. It's something that people get hung up on a lot. It's just so that we can actually simplify this whole circuit. And I can put this right here. And we have 5 volts and a ground, and it's basically the same thing as having our battery there. Only I don't actually have to draw out the battery, and I don't actually, if I wanted to, I could put plus 5 volts on each of these nodes, and it would still mean the same thing. It's just a lot simpler way of drawing the schematic. I hope that'll make sense as I move on later in later videos. I tried to draw this little doodad over here to show you if we connect the negative side of the battery to ground, we get positive voltage, and if we connect the positive side of the battery to ground, we get negative voltage out of the other end. This is just showing you that we have 0 volts, and the battery can sort of be thought of as a spacer in a number line. So that's all I had to cover for today. I hope you will continue to watch these videos. If you have any suggestions, please leave them in the comments. Don't forget to like and subscribe. And don't shock yourself.